Okay, let's see. Let's get back here. All right, so right, a lot of review, but here we can talk about temporal difference learning, and this is going to begin to kind of trade off between those extremes that we talked about. Temporal difference learning is going to emphasize rewards due to recent events, right? And that's similar to how humans and mammals learn, at least to our understanding. Something that happened recently that then created some effect, right? Cause and effect, and recently and closely correlated in time. All these things kind of lead, to stronger learning, right? And so here we're going to emphasize rewards due to recent events. So we're still going to have this value here of being in state S at a particular K, step K, and that's still going to be this expected value of R sub K plus this gamma of V. And here my notation is a little different. Instead of prime, I'm using K plus 1 here, right? But now we take one time step into the future, and so we have this V new SK, so we're going to update this value of mean in the particular state, and we're going to look at this update equation here. So this is another kind of view of that Bellman optimality equation. Here we're going to have a little bit of a learning rate. So we're going to update the old value by some fraction to get a new value, right? And so we're going to have that reward, and we're going to include this, kind of the temporal difference target estimate, right? So this is that total reward that we're looking at, right? So the reward now plus all the rewards we would get in the future, but then we're going to subtract out this one that we actually had before, right? So we measure that reward, and then we look at this as this temporal difference error, and we update our values accordingly, right? So we can extend, that was we would call TD0. We can extend some steps into the future, so we can extend this. We would have R plus another R K plus 1, so the next reward. But again, we're going to weight that with this gamma, or discount it is the term we use, sorry, by this factor gamma. And then now previously we had this the rest of the values, assuming we follow the proper or the optimal policy, and that was weighted by this gamma. But now we already pulled gamma out here for this reward, and so now we're going to put gamma squared there, but we're also going to be looking at SK plus 2, right? But then we're still subtracting out the old value that we had before at this step. So here we're just extending this so we can go n times, and if we go out to basically n is equal to infinity, then we're back to essentially Monte Carlo, right? If we take that to infinite number of steps. So, and there's a few variants on that, but we introduce this to now look at Q learning, right? So, so now if we, instead of trying to learn this value function, right? Which just tells us a value of being in a particular state. Doesn't tell us a whole lot about the action it needs to take to get to that state. Now, if we have some sort of model, we know we're in some other state, and we see that there's a maximum, a large value of being in this state. If we can figure out what action puts us in that state, great, right? But that's really what this Q function does, right? It's we're in a given state, and what is the maximum value over what is the action that gives us the maximum value, right? To go into the next state, right? So here, this again is an implementation of the Bellman optimality equation, an update equation that satisfies that. So here we're following the same concept, but we're substituting Q in for values. So if we've received a reward, then we update our Q values according to this update equation, right? And so we've measured that. This is our prior value that we had in our table. And, at about this time, you might start scratching your head. Well, wait, if we've only taken a few steps, right, up to step K, how do we know this? This stuff at K plus 1, and then, again, iteratively, recursively, K plus 2, K plus 3, K plus 4, right? How do we know this? Well, we kind of know, but we don't know with any certainty, right? So we're going to start with these things initialized. Maybe they're all initialized to 0. And so early in the training, this function here, this table, and finding the maximum A or the A that maximizes this value, we may not know that with any degree of resolution at all, right? But we're iteratively and continually updating these values, right? And as we trial and error, and so we keep updating these. And so the first time through, we're going to be updating this, but it's still going to be a horribly useless value to us, right? But over time, it's going to get better and better. And we control that rate by this alpha, because if we take some weird step, we get some weird RK, we don't necessarily want to totally wipe out the data that we've learned so far, but we're going to update it gradually, right? And so remember that this is basically updating a delta, right? So this is some sort of like delta or error function. We're adding a certain weight to that. So in some cases, we may find that our reward was not as good as we thought it was going to be, or maybe it's better than we thought it was going to be, right? And so we're going to tweak this value and keep updating it, right? So this is Q learning in a mathematical statement, right? So, but how do we do this, right? So, well, we need to define our environment, right? So we've got, in this reinforcement learning environment, we've got states and actions. Those are inputs into our algorithms, and then, states and rewards. Do I have that right? Yeah, and then our agent is going to output a particular action there, right? And we're going to build up this Q table, so values for each S and A combination by trial and error. But it's a little bit more disciplined than the Monte Carlo approach is, right? So this is what we call off policy, because as it turns out we don't always take the best um, action to give us this reward when we are trying to calculate or build up this equation, right? So we have an agent, it's going to look at what state it's in, and it's going to choose an action. And much of the time it will choose a maximum one, but it might choose a different one, right? It's going to explore around. And but so we might take some non-optimal action given the state we're in, right? Using that epsilon greedy type algorithm, right? Sometimes we'll explore. So we'll take a different action. But when we update it, we're going to update it with this maximum, this best action right there. All right, so let's look at an example here. So here's Frozen Lake. I think I tried to show this super quickly last week, and it was probably a blur, right? But we're going to use NumPy, and we're also going to use this gymnasium, or the older versions were called Gym, and but now it's called Gymnasium. But to try to keep compatibility with legacy code, we usually import it as Gym. And then matplotlib pyplot helps us plot charts and make nice pretty charts. Pickle allows us to save models in particular, or save objects to a file, compress format, and read them back in later. And RE is a regular expression type of thing. So here's that epsilon greedy algorithm I talked about before. And let me just start running these. And let's skip over SARSA for now. I'll run it just so we have it. And let's look at this QLearn algorithm. Okay, so we're going to have this function, and it's going to have some number of episodes that we're going to learn over or play the game over, basically. So we're going to have two modes. We might be training, in which case we're going to do all that epsilon greedy type stuff. We're going to update our equation, our Q tables according to the update equation, or we might not be training. And so we might train an agent in a simulation and then just want to deploy it. And once we deploy it, we always want it to take the best choices, the best decisions, right? So we would set training to false in. And this is just, we can use an 8x8 cell map or 4x4 cell map. And the 8x8 is a little more interesting, but it takes a lot longer to run. The Frozen Lake scenario here, let's see, do we have a picture of it somewhere? Yeah, here's a picture of a frozen lake game, and we'll see this as we run it. So it's a frozen lake, and the agent starts up here and wants to get to this prize down here. And this is a 4x4 game, but it has some holes in the ice, and you don't want to fall through those, right? And you can't go off the rink or the lake. You'll end up, just bounce off and stuff. So, this is the game itself. Now, to make it a little bit harder and make it more random, we can make this ice slippery, right? And so then that means you might take an action to go right here, but you might slip and instead go down or go up or left or something like that, right? So that's kind of the setup of the game itself, right? So we can decide whether it's slippery or not. And then also I have this render mode. So if you play with this a little bit, then you can either set it not to render and it doesn't try to draw anything on the screen as it runs, and it'll run really fast. But if you render it to human mode, then it'll go through some little animations that shows the steps it's making, and that's kind of illustrative or educational if you're watching it run, but it really slows things down. So if we're training, we're going to initialize, as you know, we dump into this learning algorithm to begin with. We're going to initialize the Q table to zeros, right? So we can use NumPy algorithm zeros, and this is basically the dimensions. So, oops, I'm sorry, I skipped over it. We're going to use the gym to make the game, and it's going to make an environment. And so we're going to use the Frozen Lake V1. If you look on the internet for Frozen Lake reinforcement learning, you'll see a lot of old stuff with version 0, but there's a few little tweaks to get you to V1. And then this is just passing in the parameters. I use this little construct in Python where we can do a conditional operator here, basically, kind of similar to the question mark operator in C, if you've used that before. But so if large map is true, we'll set the map to 8x8, else we'll set it to 4x4, and we pass in the rest of the parameters the same way. So we've got now an environment, and we use that environment to issue actions into it, and we step to the next time step, and then the environment will calculate the rewards and the next state and give it back to us, right? So so that might be you fell into a hole or something like that. So then all right, we just mock up a name, and if we're training, we're going to initialize the Q table. Else, if we're just operating, we're going to read in the Q table from this pickle file and then use it, right? So at the end of the training, we're going to save it, and then if we're just running or exploiting, we're going to read it in. Then we're going to initialize here a learning rate of 0.9, a discount factor of 0.9. These are just arbitrary. I haven't played with these at all. I've stolen most of this code. I'll try to give some references in Moodle, but I've created this based on some things out there on the internet. So we'll set epsilon to 1 initially here, and we'll demonstrate a epsilon decay rate. So if we set this to 1 and we take a random number, then we're guaranteed to be less than or equal to epsilon, right? So when we calculate our random number of determining, this is the epsilon greedy algorithm here, basically. So we'll be essentially guaranteed to explore to begin with, but then we're going to decay that epsilon over time, and it'll get smaller and smaller, so we'll spend more time exploiting. We just create a random number generator using NumPy, and then this is just to keep track of things for our evaluation. We're going to have rewards per episode, and we'll initialize that to 0. Then we're going to run this whole training loop some number of episodes, right? Some number of games. We're going to play this game. We're going to win or lose. We're going to record the rewards for each of those steps and update our Q tables accordingly. And then we'll do another game and another game and another game. And we might do this a few thousand times, right? So each time we start a new episode, we reset the environment. This environment reset in a newer version actually returns back a couple of an array or a list of things, I guess is the right way of saying it. So I'm just peeling off the first one, which is the state. So that's our initial state that we're going to be in, and it's going to be in the upper left corner typically, unless you customize the game. And we're going to initialize as terminated and truncated. Terminated is when the episode ends, either because we fell into a hole or because we reached our goal. Truncated, well, built into the environment is maximum number of steps. I think it's something like 200 or whatever. And so if you find yourself just wandering around in the wilderness, it's eventually going to give up on you and return back as truncated. So we initialize those as false, and now we go through a while loop. Now this is playing the actual game, right? So an episode of a game. Then we're going to repeat that some number of episodes, right? So, and so if we're in training mode and our random number generator gives us something less than epsilon, then we're going to sample within that action space, right? So action space is well, I guess it's just a function of the environment, right? An action space, you can do an action space .n, and it'll tell you the number of actions in that space, and so that's encoded into the game. And in this case, it's 4, right? So you can go up, down, left, or right. And so we're going to sample that, and the environment's going to do that. We could implement this by hand, which we did in that previous example I showed on the slides. But in here, we're going to use the environment to sample one of those actions. So this is exploring. We're going to come back with an action. Otherwise, if we're not training, or we're just exploiting, or the epsilon greedy said, yeah, go ahead and exploit, then we're going to use a NumPy function called argmax, which you've seen on my slides. And we're going to look at the particular state we're in. Remember, we initialized it up here in this event reset. And then, but across all the different actions, right? So we're going to find the maximum value out of all that and return the argument, or the action associated with maximizing that Q value. So we're returning the action that produces a maximum Q. Then we're going to step. So this is inside the environment. It's going to move your character. It's going to determine the reward. It's going to determine the new state. If it's slippery, it's going to apply those rules and all that, right? So we just pass it an action. It knows the state it's been in, right? So when we reset it, it returned back the state, but it keeps that in its internal memory, right? So it's some sort of class. And that's part of this gem library. So when we take a step, a time step, now it's going to return back the new state and the new reward. And then it'll also tell us whether we're done, the game ended, or whether we've tried too hard, too long. And this is an info structure to get more details, but I'm ignoring it. You can do that in Python just by putting an underscore there, which is just like another variable, but we're just ignoring it. So, and then if we're training, now we take that new state and that reward info, and we update our Q value, right? So here, this is that equation that we just looked at, right? So this equation here is what we've coded up in here, right? So that's a Python equivalent of that equation. We're using NumPy maximum to find the best Q value for our new state and discounting that, right? That's going to be, we've received some reward, and now this is assuming that we're going to follow the best policy from here on out, whatever we think that best policy is, based upon how accurate this table has been built to this point. But we're going to follow that and discount the rewards associated with that, right? So the Q table is essentially holding rewards, right? This is a reward we actually got back, and this is the old Q value for that state action pair, and this is going to be the new one, right? So this is our update equation. Then we update our current state to be the new state, and we keep running the episode until we're done, right? And we're updating, we're moving to different states as we do that. So we might revisit that same block, that same square. We might take a different action in that case, right? Or we might take the same action. We're going to keep updating it. And again, at first, this thing is garbage. It's giving us out garbage. But as we explore, as we play many games, we're going to get better and better information in this. Okay. Then as we finish a game, right, an episode, then we're going to decrease epsilon by this tiny amount, right? And but not less than 0, right? So we're going to decrease epsilon by this decay rate, but then we won't go below 0. And then we will, if we do get down to 0, then we'll set our learning rate to a very small number. So we're not basically learning kind of bogus information, or we don't have some instability. Now we're either going to get a reward of, I think, well, 1 is good, and I'm not sure of the other rewards, if they're all 0 or if they're less than that, right? So this will basically give us a reward of 1 if we won the game. And then we'll store that and be able to track it. Then when we're done with all those games, we'll close the environment and we'll just sum some stuff up. We'll plot those rewards, sum over time, and save that figure so we'll plot it and look at it later. And if we are training, then we will save that Q table in this pickle file, and so that we can read it in later and actually exploit, right? And then we'll return the Q table. We'll run that for now. And so now let's run this in training. So well, we're not going to slip at first, right? So we're going to run 15,000 iterations, and but we're not going to slip, and we're just doing a small map, because large map is false, right? And so this is our Q table. So along here is all the different states we might be in. So it should be what, 16? 1, 2, 3, 4, looks about 16. And these are the different actions we could take. So have to kind of remember which one is what, and how this game is, how the blocks are numbered and that type of thing. But this gives you the value that you'll receive, that you predict to receive if you take a take this action while in this state, right? So and if we look at this chart now, we see this is the number of episodes that we did, and this is the reward that we're getting. So we start off pretty poorly here, but as we build up that Q table over these many, maybe 10,000 different episodes, we get pretty good. And then once we do, then we kind of saturate that learning rate, and our epsilon is 0, so we're exploiting at this point up here, right? So all right, so that was training. Now let's set training to false and try to exploit this. Okay, so that I'm still not rendering it. So this shows that even when we try to exploit, it still takes us a little bit of time to start getting rewards. I guess this is just a kind of cumulative reward, so it's building up and all. So now here, let's render it. Let's just play one game, and you see, boom, yay, we won. So that was pretty easy because slip was false. Now, if we instead turn slip on and run that, still runs pretty fast because we have a very small map. But you see, we struggle and we never really get to that saturated reward of 100 and stuff. So if we what's the difference between here? Okay, I'm sorry. This is that was training. So we trained the new model with slip, and now we're exploiting. So again, we struggle a little bit. Let's render that. And where's my guy? Here he is. So you see the slippery factor makes it kind of hard. I'm going to run this game 5 times. So we won on that episode. But we won't always win, right? Because we know that reward isn't super high there. Oh, come on, buddy. You can do it. Yes. All right. So, all right, we'll let that run. And let's look at, that was Q learning. And let's look at, let's see, I have some notes there. I don't see the notes because I only have a single monitor here. The action we take to get the reward do not have to be the optimal action. But when we update the Q value, we do it on the basis of the optimal action, right? So I was trying to explain that. We might, when we decide the action to output, we might not pick the maximum one, right? So we might explore and pick what might be a suboptimal action to take. But when we update it, we do it on the basis of the optimal action, right? That's kind of what makes us off policy. It's always a little hard for me to keep off policy and on policy straight. But the advantage of doing this is that we can learn from experiences, so we can save up our games and our work and maybe go back and look at them in a memory and replay them and learn from that. Or we can essentially do that via some expert grandmaster at a game or something. You can imagine that like, I don't know exactly how Tesla implements everything, but they are gathering all sorts of data on the on drivers. As Tesla owners drive around, they're gathering data from their sensors and from how we react in different situations, whether we see something and we hit the brake, or we swerve, or we just keep going, right? And so now their algorithms can look at that data and learn from it, right? And it can, because these actions here that we're taking aren't directly correlated, or they're not necessarily the same as the ones we update with. Okay, so that's off policy. Well, we also have this sourcer, state action, reward state action. And there's a little bit of a difference here. And but it's particularly useful for when it's not appropriate to take suboptimal actions. So once you have your unmanned autonomous vehicle robotaxi out there driving around, with passengers and amongst pedestrians and bicyclists and other cars, you don't want to do much exploring, right? You don't want to take suboptimal actions in that case. You want to take the best action you know. Now, whether that is truly optimal or is still suboptimal, that's another case. And you are still going to gather data and maybe replay it and try to learn from it. But if you're gathering, you're running your reinforcement algorithm in the real world, not in a simulator, in the real world, and you can't afford to make mistakes, then you need to be on policy. Right. So here, this is the difference here. Instead of doing this max of the AK type of thing, right? So the SA, rather than maximizing that Q, we're using the one that we actually choose. Okay. So so this can give us a better total reward while learning, right? Because we're choosing more optimal actions in how we do this, right? So there's this last statement is a little bit vague depending upon how the algorithm's actually implemented, but we're still going to do some epsilon greedy because we still have to explore a little bit. But the idea is that we're going to start in a given state, we're going to select an action, we're going to get the reward from that, and then we're going to do some more state actions, right? So let's look at that real quick. And so here's the Q-learn algorithm. Here's the SARSA algorithm. Now I sourced this from a different code example, but I kind of mashed them up so they looked a little bit the same. So we still have a similar calling sequence, but let's see, a little bit more information that we're passing in with the alpha and the gamma. In this case, we kind of declared that inside the function, but here I'm passing that in, and also the epsilon values. So now I can control these. All right, but otherwise it's similar. We're going to create this. We're going to note the number of actions by querying the action space. And again, in this particular game, it's 4. We can make other games. And then we're going to also keep track of our rewards per episode. And now we're going to, for I and range of episodes. So this is a, I think I mentioned this in our Python primer lesson, but the way you write for loops in Python is you do this for in some set, right? And or list, and instead of kind of a basic C type for loop, it's more like a for each loop that you might see in C# or I think Java has it. It's been a long time since I programmed in Java, but and other languages, right? So here we have for in range episodes. So episodes is a scalar number. It's going to be 15,000 or 1,000 or something like that, right? And range actually returns. So this will run from 0 up to 1 minus this number, right? So range is going to expand this from 0 up to and episodes minus 1. So if episodes is like 4, the range is going to produce a list or a set of 0, 1, 2, and 3. All right, so then we have that colon, and we indent a tab here, and we create this initial state by resetting the environment. Now here, this is a little bit different. We're going to go ahead, so we have a state. Now we're going to create an initial action. And here we're going to, because we call this in a couple of different spots, we're calling a function. In this QLearn, we implemented the epsilon greedy algorithm right there, but here we've implemented it up here as a separate function, doing essentially the same thing, a little bit different coding style, but still doing the same thing. And that's the algorithm I showed in my slide on the slide deck. We initialize terminated and truncated, and then we start this while loop. So now we're starting an episode of a game. We're going to play it until the game ends, right? One way or another. So we step with that action, right? So in comparison, when we started in the Q learning, we had this action, but that came from this, right? So here we already have a state and an action, and then yeah, we step in here and we end up with a new state and a new reward, and then we call this epsilon greedy again to get a new action, right? So this is where the difference really is, right? So then we update our Q table. Here I'm using this little plus equals idiom to take the old value and add this delta to it, right? So I think hopefully that's from has a C equivalent, so there's C++ too. So all right, so now we have this learning rate alpha, and we have the reward, and now we have this discount factor gamma. Now we take this Q of this new state, right? So we are new action, right? So we took this action we had calculated up here, we stepped the environment and got a new state, right? So that's a state, action, reward, and then state and action, right? So so we take that new state and new action as our Q value instead of doing this max over the Qs, right? So we're still using epsilon greedy to try to figure out, do we explore or exploit? But we update this with what we actually did, right? So we took an action, we got an action, and then we created an action, got a new state, and then actually took that action to bring us to yet another state. Did I lose myself there? Yeah. So I'm sorry. We didn't take another step. We just created a new action based upon that, right? So and then this is that delta. We take the old one and subtract it, but all that's multiplied by our alpha learning rate. And then we just copy over. It's another thing you can do with Python. You can do multiple assignment statements in one. Here, this state will be take on this value. New action will be assigned to action, right? So we're doing essentially two statements in one there. And then again, we're collecting up our rewards and looking at the rewards per episode. So then we'll close the environment. After we've done all those, we'll close that environment. Sorry. Then we let's see, I do need to keep an eye on time. I've got a half hour to go, right? So all right, then we do our normal little thing of reporting and plotting and saving the Q table and returning the Q table, right? So I think I already ran this, but I'll make sure. The environment I'm working in is Jupyter Notebooks, and it's super handy in Python because it's maintaining all this information in memory, all the variables and that type of thing. But we can run different parts of the code separately and over again. So here we'll initialize these values, and then we'll run this. And here we get this table, right? So and we see here that it took us a while. So here I only ran, let's see, 1,000 episodes. In Q Learning, I was running, I think, 15,000 or 15,000 episodes. So it's maybe not an exact comparison, but we see that we do start to get some good rewards, and we're falling off there. But sometimes, so with reinforcement learning, you have to be a little careful. Sometimes things are a little bit brittle, and it doesn't always work out great for you. So, but here we run it, and right, is training is equal to false. So now we're fully exploiting, and here I'll turn the rendering on and see what we get there. All right, so that was a little bit interesting. I don't know if you saw that, but it slip is turned off, but he came down here and then backed up once, and then came to the ultimate reward. So maybe taking a few extra steps will decrease the reward. If we trained more, maybe it would get better. Don't know. All right, so that's SARSA, a little bit different, right? So it's on policy, and that that difference is showing up right here, where we're updating based upon the actions that we're actually taking. All right, now let's take a quick look at deep reinforcement learning. I'm going to give you some concepts here, and we might have some time to look at a little bit of code. So the basic Q learning and SARSA algorithms can be implemented using tables, but for high dimensional environments like much of the real world with many different types of actions and states, the states are implied by this high dimension. We need to do something better, right? So this is related to the curse of dimensionality. You can look that up, but basically things get much worse, much faster as your dimensions of your problem go up. And so it doesn't just scale linearly. So deep reinforcement learning essentially, super high level, replaces tables with functions which are implemented using neural networks. Again, I mentioned neural networks because all the different parameters, all the different layers and neurons in those layers, they are really good at implementing very complex and arbitrary functions. Okay, so let's look first at deep policy gradient. Note that both Q and SARSA imply discrete states and state action pairs. Autonomous driving includes many continuous situations. Policy gradient learning is similar to gradient descent in that we use in backpropagation, right? And there, as I mentioned earlier this evening, in backpropagation, we're minimizing the loss, so we're following a gradient down to a minimum cost or loss, a cumulative loss, except now we want to maximize the cumulative reward. So it's the same algorithm, it's just, you know, the sign's reversed, right? So we want to maximize instead of minimize. But it requires us taking this gradient or set of partial derivatives with respect to the parameters of the model of this cumulative reward, and then update those parameters of the model. Right. So according to this learning rate. All right. So one area that we see this is called actor critic, and here this um, uh, diagram similar to what we saw before. Initially, at the beginning of the lecture, we have an environment and an agent, except now we're going to split this agent up into an actor and a critic. So the actor is, its job is to examine what state we're in and create an action. Okay, it sounds a lot like an agent, but the agent in our previous views also looked at the reward, right? So that's a critic's job. The critic's job is taking this reward and this state and it's turning that into a value, right? So this guy's the one that takes the actions, but this critic here helps the actor choose the right action. It's kind of like a coach, right? We'll call it a critic, right? So this is the one that's taking all the actions, but it gets advised by this critic. So super high level, yeah, but that's the idea. So the cool thing is that we can implement these decisions here of deciding what kind of value we're really getting out of these rewards and states, and what kind of action we should be taking based upon that state and that value. We can implement these as neural networks to do very complex, high dimensionality type problems, right? And potentially in a continuous domain instead of discrete in terms of the action set and state set. So the cool thing is that since these are implemented as deep neural networks, there's actually a significant shared portion. Again, this is super high level, super hand wavy, but the idea is that this is some big, long, deep neural network to do the actor function, and then there's a super long, deep neural network to do the critic function. There's a good likelihood that there's a ton in common in those first few layers. Remember, we discussed a little bit, didn't go in super detail, but we talked about in deep neural networks and like computer vision and how those first few layers are trying to take pixels and create features out of them, right? So it would try to find lines, and maybe if it found some lines, then it could find some corners and that type of thing, right? And so each layer is building up a richer feature set. But just like in computer vision, whether it's image classification or object detection, you can like train a big network or let someone else do it and give you a network, and then you can fine tune it by adding on a few layers or just tweaking the last layer or few to kind of recognize the objects you're interested in, right? So maybe someone's trained it on finding cats and dogs and different animals, but you want to find cars and trucks and bicycles, right? So all those early layers are still going to do that same job, and you just need to kind of train those last few layers to take all that high level information and create a specific classification of it, right? So same type of thing here. So this is a big savings in terms of computational performance and memory and that type of thing. All right. Neural networks train poorly when their inputs are highly correlated. So, all right, well, I just put a damper on everything, right? So it talked about how, oh yeah, we can do all these deep neural networks to do all this type of stuff, right? But well, an agent playing a game is producing highly correlated data. And if we train a neural network with highly correlated data, then they end up being very brittle. They do too much memorization. They can't generalize, that type of thing. So, in you know, conventional supervised learning, we're doing things like regularization and dropout, and we're doing all sorts of things to try to avoid that, to try to break up any correlation. We try to make sure we have a very rich and diverse data set, and then we might do all sorts of different tricks to try to get around this. But in reinforcement learning, we're correlated from the beginning, right? The step I take at k+1 is highly correlated to the step I took at k, and that's correlated to the step I took at k-1, right? So they're very dependent upon each other. I wouldn't be taking that step if I hadn't taken the previous step. So what we can do to get around that is that we can store data in what we call a replay buffer memory. So as we play these games, we store the individual results of that state, action, reward, new state type of thing in this replay buffer. Then we can read those out at different times in different orders, and thereby decorrelating all that data. And we're running out of time, so that's as deep as we're going to get, except that that doesn't really work very well with actor critic. So it's very brittle in general, and adding a replay buffer does not help significantly. So there's this thing called asynchronous advantage actor critic, sometimes EECE, and so it's important that maybe you've at least heard about it, right? So instead of using this replay buffer, we're going to decorrelate all these transitions, right? The record of the state, action, reward, new state type of thing, all those different transactions. So instead of putting in a replay buffer and then trying to read it out at different times and that type of thing, we're going to instead play a large number of agents, right, in parallel, and in their own little environments, right? And they're going to be updating their neural networks, but then there's a big one that they're also contributing to, right? So that so as you've seen, when you play these episodes, these games, you don't necessarily do everything in lockstep, right? So maybe it takes you 5 steps to win or lose in one game, and the next episode it takes you 7 or 6, right? So you're not going to keep all these guys in synchronous steps while you're running them in parallel. And so we call this asynchronous. They're going to run at different rates, and that's fine. But we'll keep updating our parent model, and that's going to give us this kind of richness or decorrelation of all these transitions as we do this. And so as a side note, you kind of need to do this as different CPU threads, or conceivably different CPUs if you want to scale out that way. If you done any GPU level programming with CUDA or similar, you'll know that everything has to be kind of synchronized. Everything, all the threads have to wait on each other, and the slowest one gates everyone else. So it's a lot of tricks to getting that right. Since these are asynchronous, you're pretty much doing that at the CPU level. So, all right, so that was the end of the lecture, but let's look at code a little bit more. And here's an example of a deep network using actor critic. It's pretty simple. It's not an asynchronous advantage. Actor critic is just a simple actor critic one, and I can show you at least how it gets built up in the next 15 minutes. So we're going to import OS because we're going to do some file name stuff, and then so that's not necessarily relevant to reinforcement learning. But we're going to import Keras and also layers. We're just going to use dense layers. We're not going to do anything fancy like convolutional layers or anything like that. So they're all going to be dense layers composed of a bunch of neurons. So here I'm going to organize this as some classes, right? So here we're going to have a network class, and it's going to inherit from Keras model, right? So it's going to do some inheritance here. And this init function is essentially your constructor in Python. Okay, so it has a certain signature to it, underscore, underscore. There's two underscores there, init and two underscores. Self is essentially a pointer to the object that's created. So it's just the way Python does it. So if you're having a class and you want a method that can operate on class data, then the first parameter here is always going to be self. You would actually have that in not C, obviously, but C++, C#, and that type of thing. It's just hidden, right? It's still in there. If you like somehow dug down to the lowest levels of how it gets implemented, there's a pointer to itself in there for object or non-static methods. So we're going to pass in the number of actions and then the dimensions of our fully connected first layer and our fully connected second layer. Okay, and these are just defaults, default to 1024 and default to 512. We're going to have a name here and a checkpoint directory. So we're going to be able to save things as we train periodically. As we get something that's better, we'll save it, right? So this is calling the constructor of the init function of the parent class. And then now we're just, again, this is constructor, so we're the equivalent of a constructor for those of you who are new to Python. And so we're just going to save these parameters in as variables of the class, and then we're going to use this OS library to create a path name with a file name, and join here will make sure that you're using the right slashes, and if this checkpoint dir name doesn't have a trailing slash, it will add it. This code doesn't automatically create a folder, so if that folder doesn't exist, it'll die. That, you know, for production code, you'd want to fix that. And then we start kind of building up our network. So I'm gonna go ahead and create a dense layer with that number of dimensions and use the ReLU function, do the same thing for the second layer. And then we'll have this value and policy networks, right? And here this dense, that's just going to have a size of 1 neuron, and because it's just outputting a single value, right? And then this pi now is a policy. This is going to determine which action you're going to take, right? And it's going to be softmax, so it's going to output as a probability function. So it'll have n action outputs. Let's say it's 4, and whatever values it's outputting, they will all sum to 1. I think we did a slide or two on softmax a few weeks ago. All right, now I'm going to have a call function here that is going to bring in a state, and then it's going to propagate that state through the first layer, and then the second layer, and then it's going to output a V, and I'm going to output a pi, right? So this, we're just reusing the value variable here, right? So it does get updated, right? So the fully connected first layer produces a value as a vector, and then that's going to be passed into the second layer. And even though it's named the same, it's going to take on a new value, right? And then we're going to output V and pi there. So all right, so now that's the actor-critic network itself. Now, this is so originally this sits in different files, right? So, but we'll import TensorFlow and use the Atom optimizer, and we're also going to import this TensorFlow probability. So that's a little bit outside the main TensorFlow product, so you'll need to install that separately, but it's pip installed. So then we have a class agent. So again, we're going to declare some things. We're going to have an action space. It's going to be a list for 0 to 1 minus number, or the number of actions minus 1, right? And then we're going to have this actor critic network. We're going to create that with these number of actions, right? So we're basically calling this class here, and we're creating it, right? And using the defaults on some of these, right? And then that's going to give us this instance back, and then we're going to compile that as a using Keras here with the Atom optimizer and a learning rate that we specify, right? And then let me speed up a little bit here. We're choosing an action. We've got to do a little bit of tricks here, because observation is what we're observing from the environment, and we need to convert that to a tensor, and or essentially a vector in this case. And then we call this actor critic to return back our probabilities, right? Give it a state, and that will give us back our probabilities, right? What is it's that it's this actor critic network, right? And that's inheriting from this Keras model. So this type of thing is from the inheritance. So we're going to ignore the first parameter that it gets, first variable it gets back, but we're going to look at these probabilities, and we're going to kind of convert those to action probabilities through this tensor flow probability function here. All right, let me just skip over some stuff so we have time to finish. We got save model, load model, and here's the learn. So this is the important part. Here we're going to take the state and old state, new state, and reward, and convert those to tensors. There's just some bookkeeping stuff. And then we'll do this gradient tape, and as with this as tape, and then we can use that throughout here. And yeah, sorry, I'm gonna run out of time. So here we get the state value and probabilities from the old state, and then we get this from the new state. And then we get the action probabilities. We create this update reward function. We declare a loss function for the actor, and we create a loss function for the critic. That gives us a total loss. Remember, we need to train this neural network as we're doing that, right? And so then we calculate the gradients and using the loss, and then we apply the gradients to the model, right? So let's see, let me start running this stuff here real quick. And here, this is now main thing. We're going to run this cart pull game, and it's training right now. And the cart pull is trying to balance a hinged pull on a cart that moves left and right. So that pull has some height, and if you just sit there, it's just going to fall over, right? It's hinged, it's going to pivot, and it's going to fall over. And so, oh my, this is going to take forever because it's going to run for lots of episodes. So, all right, yeah, I lost it when I had to restart Chrome because of the permissions issue. So I'll upload these scripts to Moodle, and you'll be able to download those and run those. And let's see if we can do a little learning experiment on this. But it is, if you turn rendering on, you can watch it try to balance that pull. Right now I have render mode none, but if you just uncomment that and wipe that out, you'll be able to see it run as visualization. It will actually animate that cart and show it. So, all right. So this is going to run to many episodes, and it's going to take a long time. How many episodes are we running here? 1,800, right? So, and we're up to 158. So maybe I'll show that next week. So, all right. I guess that's gonna be it for this week. And so if you have any assignments you're behind on, you need to get those updated as soon as possible, because I gotta grade and move on. I mentioned that last week, and I'm just reemphasizing it this week. So, all right, that's it. Have a good week.
Thank you. Have a good
Thank you, Professor. Have a good week.